Om Swastiastu, sebelumnya perkenalkan nama saya Tjokorda dengan NIM 22055531150. Di sini saya akan menjelaskan Science of Engineering Materials tentang cross-linking of polymer chains and stereoisomerism of linear polymers. Nah, sumber referensi saya berasal dari buku Science of Engineering Materials volume kedua yang ditulis oleh Manas Chandra. Berikut adalah daftar isi yang akan saya bahas di dalam presentasi saya. Yang pertama itu ada cross-linking of polymer chains. Yang kedua ada stereoisomerism of linear polymers. Dan yang terakhir ada crystalline out and amorphous behavior of polymers. Yang pertama, yaitu cross-linking of polymer chains. Dalam kondisi khusus, molekul rantai polimer dapat dihubungkan silang oleh atom atau kelompok atom yang membentuk ikatan polimer antar rantai. Hubungan silang dapat dibentuk oleh atom atau molekul asing, misalnya atom sulfur dalam karet vulkanisat. Tingkat keterkaitan silang yang tinggi menimbulkan polimer jaringan 3 dimensi atau ruang angkasa di mana semua rantai polimer dihubungkan bersama untuk membentuk satu molekul raksasa. Dengan demikian, alih-alih terdiri dari molekul diskrit, sepotong polimer yang sangat berikatan silang membentuk hanya satu molekul. Yang kedua yaitu stereoisomerisme polimer linear. Karet alam dan sebagian besar karet sintetis tidak jenuh dan memiliki ikatan rangkap C9C di sepanjang rantainya. Misalnya, setiap merisoprena dalam karet akan alam memiliki ikatan rangkap di tengah. Itu adalah contoh rumus umum polimer vinil. Di sisi lain, karet alam yang merupakan cis polisopren bersifat amorf dan elastomer pada suhu kamar karena hambatan sterik dalam konfigurasi cis kontribusi pada orientasi acak dan kekaburan rantai polimer. Selanjutnya kita akan melihat video tentang pembuatan karet sintetis.
Synthetic rubber reinvented the wheel. We're talking about the rubber tire. Tires for all kinds of vehicles are now made from it. This man-made material is also used to make everything from garden hoses to golf balls. Manufacturing synthetic rubber is now a computerized process, one that takes place under the watchful eye of a control room operator. He monitors numerous computer screens and live camera images. The plant itself is 437 yards long. There are a dozen or more enormous storage tanks for the raw materials, as well as several reactor units. The raw materials include a petroleum-based liquid called butadiene and solvent called hexane. They pipe these ingredients through columns to boil off any residual water, essentially purifying them. This is a laboratory demonstration of what happens next. They combine the purified butadiene and hexane and add a catalyst. The catalyst triggers a reaction that changes the chemistry. The mix becomes polybutadiene, a kind of synthetic rubber used to make tires. Adding another catalyst stops the reaction at just the right moment. The white milky liquid that exits the tank is synthetic rubber. They now pump in chemicals to tailor the rubber for a specific use, in this case, tires. The additives will increase traction and improve wear. A mechanized whisk stirs the additives into the liquid rubber. They pipe the synthetic concoction into insulated storage tanks. Inside, pumps mix it constantly so the additives don't settle on the bottom. Here's a close-up look at the liquid synthetic rubber in a laboratory beaker. It looks like a big vanilla milkshake, and it's about to be coagulated into crumbs. Here's where it all happens. This coagulation unit is like a big kettle. They pipe in the liquid rubber, a solvent mixture, and water. As they boil off the solvent, the rubber coagulates into crumbs the size of beans. The water remains because it has a higher boiling point. The mix of water and rubber crumbs bounces about in what's known as the crumb tank, until it's time for more processing. They then pump the mix into a rotary sieve. As it spins, it drains off the water. They add more water to cool the rubber crumbs. The rubber and water mix gushes onto a conveyor, which is a vibrating sieve. As the crumbs bounce along, the water drains off through the perforations in the conveyor. The synthetic rubber is now a lot like wet snow. Next, it's into the lab where they aim a beam of infrared light through a sample to analyze the microstructure. If it's acceptable, production continues. A screw-like mechanism presses the wet rubber crumbs against a metal plate to squeeze out more moisture. Another trip on the next vibrating conveyor drains off droplets. Then it's into a quivering spiral conveyor. As the synthetic rubber travels upwards on the spiral, hot air is piped in from the side to dry it. Now mostly devoid of moisture but still sticky, the synthetic rubber crumbs head down a chute and into a baler machine. This machine uses pressure to compress the crumbs into big bales. The bales of synthetic rubber head down a conveyor towards a quality control inspector. This inspector examines them for imperfections. Once he gives them the okay, they head to the packaging station. As they travel through a curtain of plastic film, machinery heat seals it around them. These bales of synthetic rubber have taken about 6 hours to manufacture. And this purely chemical creation isn't much different from the real thing. Like natural rubber, it can be melted and shaped into many different things. Soon, this batch will be turned into tires. And that's when the synthetic rubber
Behavior of polymers. Beberapa polimer benar-benar kristal dan beberapa amorf. Kebanyakan polimer memiliki karakteristik padatan kristal dan cairan yang sangat kental, seperti pola difraksi sinar X dan difraksi elektron yang menunjukkan ciri-ciri padatan kristal serta difusi cairan. Nah, sekian dari presentasi yang saya sampaikan. Saya ucapkan Om Santi 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 Santi.